Good afternoon, everyone. My name is Yuan Xin, and today I'll be presenting my CS274 final research project, which is enhancing novelty in LLM-based playlist generation. So let's start with the problem definition. My problem is actually to firstly generate a playlist of songs from playlist title. So it is actually based on Enzo's a language model-based playlist generation recommender system, where the original work employed k-means clustering and fine-tuning with cross-entropy and triple loss of the playlist dataset. So actually, the final recommender system get the top 50 frequently occurring playlist name and chose the top 10 frequently occurring songs. And then the problem of this approach of the final recommendation system is that there's a Matthew effect. Mm, Actually, for the Enzo's paper, it is actually quite innovative because it is the first paper to actually explore generation of playlists of songs just by the playlist title. Previous works actually all encompass of having a playlist of songs already, and then we are trying to generate playlist title from that. So actually, this paper was actually the inverse of the previous works that were already done. So what is Matthew effect? So Matthew effect is actually when the rich gets richer. So actually the recommendation system favors the more popular songs because we're taking the top 50 playlist name, and then we actually getting the top 10 frequently most occurring songs. And then this actually results in similar playlist names such as workout and gym that may produce actually similar playlists of songs, even though they are actually a bit different. But this presents some problems because we expect the recommended songs to be actually different, but then they might produce both the same songs, which are not which might not be what the user actually wants. So there's a need to introduce more novel metrics to actually factor in novelty of the songs being recommended rather than just the frequency of the songs. Yeah, so this architecture diagram is actually the original paper. So we firstly train a fine-tuned language model using the Spotify's million playlist dataset. And then we get the embedding representation of the songs. And then they are ranked based on cosine similarity. And then the top 50 most relevant playlists are gathered. And then there's a voting mechanism which we get at the top 10 frequently occurring songs. And then yeah, so we get the N recommended tracks, which is just top 10. So how is this relevant to web intelligence? So firstly, this paper actually contributes to the advancement of intelligent recommendation systems. So our paper leverages on large language models, which is artificial intelligence for better recommendation system. And secondly, it's using human-centric artificial intelligence and personalization. So we hope to create a more user-friendly and user-friendly recommendation system. And actually, this results in improved user engagement experience when users get what they actually want from the recommender system. And lastly, applying artificial intelligence in highly interconnected digital environments. And then web intelligence equals to artificial intelligence in the connected world. So we're leveraging on artificial intelligence to um we're leveraging on artificial intelligence to yeah, we're leveraging on artificial intelligence for the recommendation system to be more user friendly and in a highly connected world such as today. So the experiment setup of this paper actually introduced two methods. Firstly, the popularity penalization and maximal marginal relevance. So this slide will cover the popularity penalization and maximal marginal relevance. So for popularity penalization, the score is actually the sum of the similarity of the song with the query times 1 over the log of the 1 plus popularity or the frequency of the occurring song. And then it is to the power of alpha, where alpha we could control so that um we'll control the value of alpha so that if we want to have more weightage to the popularity, we could increase the value of alpha. And if we want more novelty, we could just decrease the value of alpha. Yeah, so actually we had to 1 plus because of what if the popularity is 0, right? So log 0 actually does not give a defined answer. So we have to do a log 1 plus. And then why it was inverse is because it's actually why it is why we use log, because so like it's like the real world where like the increasing from 1 to 10 it has a higher weightage, and then from 10 to 1000, so that it captures the effect of the popularity. So the popularity importance gets lower as the number of popularity increases. And then for maximal marginal relevance, this is the formula. So actually there's the lambda value where you control the similarity. So the first similarity is actually the recommendation with the query, and which is also balanced with the second similarity, which is the similarity of the recommendation with other recommendations. So yeah, this is actually trying to maximize the novelty of the recommendations too, by taking into account the similarity of between the recommendations of the songs. So the experiment setup is actually to measure the Jakarta similarity of songs recommended for workout and gym. And then for popularity penalization, the alpha value we tried was 0, 0.2, 0.4, 0.6, 0.8, and 1. So 0 is actually the baseline where it is as if there was no popularity penalization, which is the exact same as the original paper. And then for maximal marginal relevance, the lambda value we tried was 0, 0.05, 0.2, 0.4, 0.6, 0.8, and 1. So for this metric, actually 1 is the baseline. And the data set we used was the same as the original paper, which is the Spotify's million playlist data set. And then for Jakarta similarity, the formula is actually given below. So it's actually the number of sets that intersect over the number of sets that they are together. So so this is the results for popularity penalization. So for alpha equals 0, which is the baseline. So for workout at gym, you could see that the Jakarta similarity is actually 0.3, because we see that there are three overlapping songs: Power by Kanye West, Till I Collapse, Eminem, Humble by Kendrick Lamar. And then when we increase the alpha value to 0.2, you could actually see that the Jakarta similarity actually decreases. So now there are only two similar songs. And then 0.4, 0.6 is still the same Jakarta similarity, but we could see some differences in the recommendation of the songs. It becomes more and more novel. And one, finally, there's no recommendation, no similarity. So yeah, analysis of popularity penalization. So we could see that as alpha increases, the recommended songs increase in novelty. So too low of an alpha, it results in a Matthew effect, but too high of an alpha, recommended songs are too novel. So it's actually a balance between novelty and the Matthew effect. So we felt that 0.6 to 0.8 is optimal, so that Jakarta similarity is lower at 0.2 or 0.1 without compromising the relevance of the recommendation. So this is the result for maximal marginal relevance. So we could see that for lambda equals 0, the Jacob similarity is actually 0.1, which is quite low. Because 0 is actually the highest novelty for this metric. Then for 0.05, you could see that Jacob similarity increases to 0.2. For lambda equals 0.2, we see that it becomes 0.3, the Jacob similarity. And for lambda equals 0.4, we see that the Jacob similarity is also the same as 0.3. 0.6, 0.8 is the same. And for 1 is also the same. So the analysis of maximal marginal relevance is that as lambda increases, the recommended songs increase in similarity curve, but decrease in novelty. So this is actually the inverse of the previous problem, previous metric. So too high of a lambda, we get the Matthew effect. Too low of a lambda, recommended songs are too novel, may not be relevant. So we feel that 0.05 lambda is optimal, and Jacob similarity is lower at 0.2 rather than the baseline of 0.3. So the limitations of this paper, these two metrics is that so what is the optimal value of lambda and alpha, right? So there will be more experiments needed to include human feedback, possibly. Like we need to have a practical trial and then gather the user feedback on which recommendations they really like the most, so we could determine the optimal lambda and alpha value should this become a reality. And then there are only two playlist titles being considered. Yeah, so yeah, in reality there may be other similar playlist titles, but yeah, so further more experiments are needed for the real implementations. So actually, even though we have those two limitations, so actually this paper presents, even though we have those two limitations, it's still a promising direction for the implementation of algorithm, as we can see that it actually helps to solve the issue of Matthew effect, and then we can increase the novelty of the recommended songs. It provides a more robust and complete recommendation system. Yeah, so the final thing is that we need more feedback from users should this be implemented in the real world scenario. Yeah, that's it for me. Thank you.